Mathematical modeling, the Lotka Volterra population model. So two of these population models have already been covered by videos in this series, and now we're on to the final model. So we're looking at three models which progress through the system using ecological systems. We started at the very basic, and now we are adding conditions. The first two are the Malthusian and Logistic. They only deal with one species. The Malthusian has a constant factor of growth rate, and the Logistic has an intrinsic growth rate, an initial growth rate, which reduces to zero once the carrying capacity of the environment is reached. The Malthusian has a food supply which is increasing but in a linear pattern, and the population collapses once it exceeds the food supply. In the Logistic, the environment has a carrying capacity at which the population size levels off, and we end up with a horizontal graph. Now the Lotka Volterra population model takes the Logistic and adds a predator to the system. In other words, we now have two species. The growth rate is variable in both, depending on the food supply. The prey need the basic food supplied by the environment, so very similar to the Logistic. Numbers are affected, though, by the predator. And the predator population is dependent on the prey population numbers for its food. The discrete two-species Lotka Volterra population model. Being discrete, once again, it's fairly complex to calculate, where you need to calculate each in turn before carrying on. So one of the factors affecting population change in any species is the presence or absence of other species which either hunt them for food or provide them with a food supply. So this is involved with a relationship between a predator and a prey. Notice the rabbit or the hare and the fox. The model states, first of all, now these are the basic statements of the model conditions. Each prey gives rise to a constant number of offspring per year. In other words, there are no other factors limiting the prey population growth apart from predation. Each predator eats a constant proportion of prey population per year, meaning that if you double the prey population, you will double the number eaten per predator. And that does not matter how large the prey population is. It's still the same ratio. Predator reproduction is directly proportional to prey consumed. So in other words, a number of prey consumed results in one new predator. So a certain number of prey consumed gives us a new predator. Or one prey consumed produces a fraction of a new predator. And a constant proportion of the predator population dies per year, whatever the reason. So the predator death rate is dependent on the amount of food available there. It also assumes that the predator species is totally dependent on the single prey species as its only food supply. Only a single prey species. The prey species has an unlimited food supply. and there's no threat to the prey other than the specific predator. And there's a summary of the conditions. Prey, constant reproduction, unlimited food supply, predator only, threat. Predator eats a constant proportion of the prey, birth rate proportional to the prey consumed, constant death rate, and the prey is the only food supply. And the prey would grow in accordance with the logistic model. There's the logistic model, where R is the prey population, A is the intrinsic, only the initial reproductive rate, in other words, growth rate of the prey population, and K is the carrying capacity of the environment. Take note though, there's the mathematical modeling, the logistic population model. There's the formula, and if you look at the formula, there are different variables. It's very strange this, but the variables have changed, but P there stands for prey or whatever. The only thing that is the same is the K, but R before the intrinsic growth rate is now A, and P before is now R. You'll see in a moment why. So in the presence of predators, growth of the prey's population would be reduced due to the predator's consumption of prey, but it depends on the number of predators and number of prey. So we're going to reduce the prey's population. There's the prey's population. We're going to reduce it by a product of the number of prey, the number of predators, and the per capita attack rate of the predators on the prey. So we need to know those various formulae. So reduce it, so we're going to subtract, and then a product of these ones. And here comes the explanation as to where the R's and the F's come from. Rabbits, foxes, it's as simple as that. There's the prey, the rabbit, there's the predator, the fox. So we get our R's and F's. Hopefully it is logical. This number of kills is going to depend on the number of hunters and the number of those available to be hunted. That's why we have both. Number of hunters, the number available to be hunted, and then there's some factor in there on the attack rate. So there is the formula for the prey. Now we need to go on to a formula for the predators. Now in the absence of prey, if there are no prey, the predator population would decrease due to lack of food supply, as in the Malthusian model. There. So we're going to take that and change it to there, where, notice, there we are. It's very similar. There's a negative instead of a positive, and there's a C there. F is the predator population. That's the natural death rate, because the only change is the real change. Well, there is a growth rate as well, but the change here is the natural death rate of the predators. In other words, how much they die. So we need to subtract in order to get this equation. Very similar to depreciation. Now this is talking about in the absence of prey. In the absence of prey, the population cannot grow, because remember, the growth is directly proportional to the number of prey consumed. Now we're going to take that, there it is there, we've multiplied it out. So I'm going to take it to there, and then we're going to slot in this additional factor here. So in the presence of prey, this is in the absence of prey. In the presence, the predator population would increase in the same way that the prey population reduces. So there's the reduction, BRF. So now it's increasing in that same proportion, except there's a new factor here, being sort of an effectiveness. So there's the predator population. There's the prey population. There's the per capita attack rate of the predators. We're used to these. We came across them in this formula as well. And then that is the efficiency with which the predators can turn kills into food, good health and breeding. So that is a factor per species, and it depends on the species as to how effective what good their kills can actually do in terms of food, good health and breeding. So there is our formula for the predator. So we have a prey formula and a predator formula. You don't need to memorize those. Those are on the formula sheet or information booklet. But you need to know what they stand for. Now, let's have a look at an example. And just a note here, being discrete values defined by a recursive formula, it's actually quite useful to use Excel because you can put in a formula and copy it down. So here we are. Quite simply, the following information is given for a habitat containing rabbits and foxes. Now, all we've done is given all these factors. There they are there. There's the effectiveness. That's the predator food efficiency. So in other words, they're at 0.37 efficiency for turning that into growth. So here's some questions. Create a spreadsheet from N to 500 to model the rabbit and fox populations. Use this information to draw a graph of population sizes, FNRN, versus the cycle N. Now that can easily be done in charts on Excel as well. I'll show you how to do that. Does the population tend to an equilibrium or a stable point? If so, what is it? We look at the graph for that. Describe the oscillations in the data. We do the same. And project the long-term consequences of oscillations for both populations. That's also indicated by a graph, but a different graph, all drawn by Excel. So as an aside, let's have a look at this Excel bit. Excel lends itself well to setting up a general spreadsheet into which you can enter values. Here's a possible spreadsheet. There the formulae, just to remind you, that's no formula in Excel, that's just a straight printout. There's our input values. The various variables, there is the printout. These aren't the same as the question that was asked at this stage. And then here are the formulae. This first one here at cycle 0 copies directly across from the R to there, and this one here, that 8, copies directly across to there. But from then on, it's driven by formulae. And these graphs draw off this information. You'll notice this one here is the population versus time, and that is the prey population and the predator population. And then this one here is the predator versus prey. We're going to look at both. That one's asked for first. There the formulae, data input, and the cycle data output. And it's so useful because all you have to do is change these values. These values automatically change and the graphs change. Let's have a look at the formulae. This one here just says B7 because it's the cycle naught for the R. That's cycle naught for the F, so therefore it's going to be B8. Here's where the formula comes in, and that actually is this formula. If you look carefully, you'll see it's this formula here where D17, but that refers back to this one because remember that's Rn. So you'll see D17 here, D17 again there, D17 again there, and D17 again there. The A, there's the A in B10, so there's B10. The K, the carrying capacity, there it is there, well, that's on B9. So you can copy this formula easily yourself into an Excel document. B, here's B, the predator attack rate, 0.01, and that's B11, so therefore B11. And F, N, well, in other words, that there, E17, there it is there, E17, E17, it's the E. Now notice these dollar signs. If you're not totally used to Excel, these dollar signs are to stop it from progressing. For example, if you had B10 without the dollar sign, then as you drag the formula down, this will change 11, 12, and so on, but you need it to stay on B10. If you dragged it to the right or left, it would change the letters of the alphabet. You don't want that. If you want to drag to the right, you want it to stay as B. The dollars in front of these letters aren't as important. They're particularly important in front here. This mustn't have a dollar because as you drag it down, this refers to D17, and now the next cell down must refer to D18, which it will do because it doesn't have a dollar sign. And the next cell down should refer to E18, not E17, which it will do because there's no dollar sign, so it will progress. And there's the formula. There's the formula for the predator, the foxes, the F, and similar setup. Pause and have a look at it if you so wish. Let's go back to the question. Create a spreadsheet from 0 to 500 to model the rabbit and fox populations. What I've done is I've gone far beyond 500. I've gone to 15,000 just so that I can show you patterns. So, first we enter the prey population, and we enter the predator population, and then we enter the other values downwards, and automatically these formulae will work. Now, the next question says, use this information to draw a graph of population sizes F and N versus the cycle, which is N. So how do we go about that? In your Excel spreadsheet, highlight the cycle. There we highlight across there and down, R and F columns. Then we go to Insert, Scatter, that means Scatterplot. When you click it, you automatically get this drop down. And now we're going to click that one because that's the two separate graphs. We're going to click that one there, and it gives us the graph automatically on the system. You may have to get used to the formatting systems. There are various formatting systems. You have to click various areas. For example, here, if you click on there, you get the one graph's formatting. You must remove any fill, scatter fill, and scatter lines, and leave only lines. You'll see that. Say no line for scatter fill, anything to do with scatter, because otherwise you get those bigger blobs as you saw in my earlier diagram, which I had there just for the effect. So, if we have a look at that, the question now 3 says, does the population tend to an equilibrium or stable point? If so, what is it? But if we have a look, these oscillations are getting bigger and bigger and bigger, and there's no sign. They seem to be going up. The maximum seems to be in a linear pattern. And the same thing with these ones. So the blue is the foxes, the black is the rabbits, and they're both increasing. So there's no stability. While oscillating, the numbers of both appear to be diverging, in fact, just getting bigger and bigger. So describe the oscillations in the data. So let's have a look at the actual oscillations. Now what I've done is I've taken from 0 to 300. So I've taken 0 to 300 alone. I've taken that bit and I've a magnified version. Magnetized would be quite attractive, I guess. Magnified version of this graph. There it is there. Blue is the rabbits and red is the foxes. Now the size of the rabbit population is affected by the increasing fox population. Notice the rabbits are dropping at this stage because the rabbits are increasing. Then they bottom out there as the foxes are dying out again now, because the foxes start dying, they start depleting because there's not enough rabbits for it. And then it's starting to climb again because of the lack of lack of foxes, and it climbs and climbs, but now at this stage the foxes are now climbing again, so the rabbit population peaks out and goes down. There's a lagging effect in both cases. Let's have a look at just this case. This region here indicates the period of increase in the rabbit population. So from there to there, the rabbits are increasing. It starts when the fox population is in decline. So the foxes are in decline due to a shortage of rabbits. As the rabbits increase in number, a stage is reached where the fox numbers start to recover. So as we get more and more, gets to a stage where the foxes can now recover because their food supply is replenishing. But then, of course, when the foxes reach some critical stage, the rabbit population starts to decline. And for quite a while, they still supply food, so therefore the foxes are going to keep climbing. If we have a look now, this goes for the foxes increasing, the foxes at the bottom. All right. For a while, both are increasing until the reproduction of the rabbits can no longer sustain losses due to the fox kills. The fox numbers peak where the rabbits are on their way down. So this is almost like a critical point at which it's always the same place, same number of rabbits. So it seems when there are about 18 rabbits, they can no longer sustain the foxes and the fox numbers start dropping. So let's project the long-term consequences of the oscillations for both populations. So I'm going to do the R versus F graph. For 23 time periods, you see there's the starting point, 50 rabbits and 6 foxes. Now you'll notice that as time progresses, the foxes are going to climb and the rabbits are going to decline. Notice this isn't time, so I don't think a progression to the right. These are just a series of points in a scatter plot. Foxes versus rabbits. Now, there the rabbits are at a minimum and the foxes are declining. See, the rabbits are at a minimum because at this stage they're going to start increasing again to the right, and the foxes are on the way down. Now the foxes are at their minimum and they're about both to increase. There we are. And the cycle is completed. To repeat with mild increases in both populations. You see it's ended here instead of over there. So it's slightly further along, so there's slightly more rabbits and there'll actually be slightly more foxes. And that's at 152 time periods. Notice now I've added another cycle to there and it's going outwards again at 300 time periods. 453, we've had another cycle. Add another cycle, 605, 758, 911, and 1065. You'll notice that we have a number of cycles, but they're going outwards. Let's project a bigger picture of this. Let's take that. Well, it's a smaller picture, but bigger numbers. There's what we have so far. So that's what we had there, 1065, and we're taking it so we can compare. Now we're going to look at 5,000, still going outwards. 10,000, 15,000, and it's very clear that's never going to stop. So whereas before the rabbits were at 60, now they're pretty close to 140 by the 15,000. So in the long term, while there are oscillations, interesting graph, it's clear that both populations, maxima, are on the increase. And of course that means the general population of both species in the habitat is going to keep increasing without check. So now let's have a look at the Excel spreadsheet again. What we're going to do is we're going to play with it, change a few parameters and see how the graphs change. I'll tell you why I'm doing this is that most examination questions are centered around the graphs. You need to think about the graphs and what's happening. That's why I'm doing so much with the graph. Right, so there we have a situation at the moment. Now, it'll keep increasing, we know that. Now what I'm going to do is, if we change F, the predator food efficiency, decrease it, let's see what happens. You can try other ones too, but I'm going to change the F and watch how the amplitude reduces. So I'm going to make it 0.27 there instead of 0.37. And notice the new graph, instead of climbing now, the maxima are now decreasing. Instead of climbing for the foxes, their maxima are also on the decrease. So now just by changing their predator food efficiency to there, we have a very different situation. The amplitudes are now decreasing, so the amplitude of the graph is on the decrease. Remember amplitude from trigonometry, the distance it moves away from its center line. Like the amplitude there is virtually 20 from 10 up to 50. Now, very different rabbits versus foxes cycle graph. Let's have a look at those round cycle graphs with this information. Notice there, now look at the starting point there. Similar graph, but look where we've ended up. We're going inward instead of outward. Now, if you look at this, we say, well, where's it going to end? Surely at some stage it's going to end. Yes, it will. It's moving inwards, and at some stage a point of equilibrium will be reached. Finally, if we have a look at this, if we change to 0.1, have a look at this one here. There's your 56 there now. And have a look what's happening to the cycles. They're going inwards very quickly. And right in the middle there is a point of equilibrium where they now 67 rabbits, 5 foxes, and forever onwards after 1661 cycles, the foxes and rabbits will stay at that number.